Is it streaming?
I think so. Yes, it says. I'm just trying to confirm on my other window. There we go. Okay.
Great.
Okay. Hello, everyone. I'm Max New, and I'm co-organizer here with Sam Lindley, and welcome to the 8th ever and first virtual workshop on mathematically structured functional programming. As you know, it's a workshop on the applications of theoretical computer science and mathematical techniques to programming tasks. And we have a good lineup of talks. We're spreading it out over 2 days to reduce the Zoom fatigue and, make it a little better for American and European audiences. So a couple notes on the technologies we're using. So we're on Google Meets now, and I'm streaming everything on YouTube as well. Each session will have a different YouTube stream. Those are all listed on the website in case you have any issues with Google Meets and want to use that instead. You should also all have been invited to the Zulip forum for the workshop, and we'll have information there as well. And so for all of the talks, you can either ask questions in Zulip or in the Google Meets comments, and maybe the YouTube comments too. I guess I'll look at those as well. Just as a protocol, they had a nice protocol at ICFP, which is if you'd like to ask the question yourself on Google Meets, you can just prefix it with Q colon. But if you would just like one of the moderators to read the question for you, you can just write SQ colon for a silent question. And then the chair of the session will read it out for you. In case you're not on the Google Meet or just prefer not to be on the video. Okay, and with that, let's get to our first keynote. So our first keynote speaker is Pierre-Marie Pédrot. So Pierre-Marie completed his PhD in 2015, I believe, from Paris Diderot on the computational aspects of the dialectica construction. And since then, he's worked on a variety of topics, applying things like effects, independent type theory, and also taking a syntactic or type-theoretic approach to many topics in category theory and model theory. So it's a great fit for our workshop here. And today he's going to talk about some syntactic approach to working with Presheaves. So Pierre-Marie, I'll send it off to you.
Thanks a lot for the invitation. I hope my network is not going to fall during the talk. If that happens, please bear with me. So today, indeed, I will be talking about a syntactic model Presheaves in type theory. The object of my study is called CIC, the Calculus of Inductive Constructions, and it's a perfect fit for MSFP because you can either see it as some kind of very powerful intuitionistic logical system that gives you a very rich logic and a first-class notion of computation that is built in the logical system. So that's really a very powerful logical system. But at the same time, the calculus of inductive constructions is also a very powerful programming language of the functional kind, up to the point that actually you can see the types are dependent and they can be used to actually prove properties about your program, so that you can actually prove that your programs are bug-free thanks to the rich type system. But the cost of this type system is that there is no clear separation between runtime and compile time. That is, you have the dynamics of the program that are leaking in the type system. This richness, both from the point of view of logic and programming, led me to the statement that actually this is really the pinnacle of the proof as program correspondence, the Curry-Howard correspondence. And if you have trouble imagining what this system is, just picture the cock proof systems, and this is essentially the system that is underlying the cock proof system. So type theory is not something that comes out of the blue. You need a few checks for it to make sense. So the first one, and probably the most important, is that you want your type theory to be consistent in the sense that there is no close proof of falsity. So you ensure that the logic is fine. But that's not enough. You also want more from it. First, because you want to use it inside proof assistance, you want your type theory to have decidable type checking. This is kind of important. But since you also want it to be a programming language, you need a bit more properties that you wouldn't ask from a simple logical system. So first, you ask that, for instance, a proof of an integer needs to be an actual integer. And assuming that you have a way to compute, which is kind of critical if you think of your type theory as a programming language, then you want this reduction system to be consistent with the equational theory of the type theory. And for this, the two things you really want are normalization, which says that you can reduce term and it's going to end, and subject prediction, saying that the reduction procedure is compatible with typing. And obviously, these properties are somewhat interdependent, because, for instance, if you have normalization, you get canonicity. But I'm not going to talk too much about this. So what we want to do is to pick the calculus of inductive constructions and extend it with new logical and computational principles. And for this, we need to design models so that we check that these extensions are actually satisfying the good properties I was talking about before. And the subject of today's talk would be a very specific family of models, which is called Presheaves. So they are known under a variety of names. You can see them as some kind of proof-relevant cryptic semantics, if that speaks to you. They are also known as intrusionistic forcing, and there are, I think, a few more names that you might have been acquainted with, which I'm not going to mention here. But the important thing is that Presheaves are really everywhere. You can use them for a lot of model constructions in type theory, for a lot of stuff. So, for instance, cubical type theory, model type theory, you want Gaussian type theory, you can build normalization by evaluation models out of them. So really, you can find them everywhere. And what is a Presheave? It's a very simple construction in terms of category theory. You pick category P that we'll call a base category, and a Presheave over that category is just a functor from P up to set. And the main result is that Presheaves equipped with natural transformation as morphisms form a category. So it's not very interesting per se. Actually, the Presheaves form a topos. And I'm going to hand wave quickly through this in the next slide so that you get an intuitive idea of what a Presheave is. So what is a Presheave? So an object, so I said, that was a functor over a base category. So essentially, if you unfollow the definitions, a Presheave is just a pair of two things. First, a family of index sets whose indexes are the objects of the base category. And furthermore, a family of restriction morphisms that says that if you know that Q is below P, that means that there's morphisms from Q to P, then you're able to cast AP to AQ. This is the typical monotonicity that can be found in cryptic models. You want your type to be monotonous, and because here we're proof relevant, then we want this to make sense with stuff that is more than an order. We want to have a full category. And you can really see this theta A as, yes, lowering. So you see that Q is somehow below P, and theta is lowering its arguments AP to AQ along the alpha from Q to P. You want a bit more. You want this to satisfy the equational property, to be compatible with the equational properties of your base category. So essentially, if you lower along the identity, you didn't do anything. And if you lower along the composition of two morphisms, then that's the same as lowering first along the first morphism and then along the second morphism. So this is really, the restriction morphisms are just saying that lowering is compatible with the categorical structure on P. Right, What about morphisms? So a morphism is natural transformation. So if you unfold the definition, that means that you get a family of p-indexed functions, fp, from AP to BP, so the underlying sets at each point. And you furthermore require a naturality property on this family of functions. So essentially, you want theta to commute with f. So if you if theta b on alpha applied to fp at x is the same as f applied to theta x, right? So this is usually written down via this nice diagrammatic equation. So this is really saying that there are two ways to go from AP to BQ. Either you lower and then you apply F, or first you apply F and then you lower. And the two things need to be the same. Right, so these are the morphisms in the Presheaves category. So it's very well-known fact is that Presheaves actually form a topos. But for our purpose, it's not really not very interesting. This is just some kind of a categorical curse word that is very fashionable amongst categorists. But what interests us is that actually Presheaves form a model of the calculus of inductive constructions. And I'm not going to into the details, but essentially the idea is that if you have a type A, so A as type, then you interpret it as a Presheave, as a type interpretation. So double bracket A needs to be a Presheave. And if you have a term M of type A, then you give a single bracket interpretation of M, that is a natural transformation from 1, the unit Presheave, to the translation of A. Okay, so I'm not really entering the detail, but that's the big picture. And the first thing you should be observing when I wrote that is that I used set theoretical notations. I have a membership notation in the middle because all of these constructions are living in set theory. Okay, let's look at what I asked about the good properties of type theory at the beginning. So the Presheaves model, what does it give you? So it's consistent. It's very easy to check that there is no proof of false, so we're happy. Canonicity is kind of already problematic because if you have a term M of type nat, then you know that through type theory, so you can invoke the full power of type theory, M is actually equal to some integer. So if your set theory is classical, then that doesn't mean much. If it's intuitionistic, then you can actually hope to extract something out of it, but it's not ideal. Type checking is clearly not decidable because you have the full power of ZF, as I said. And way worse, there is no reduction in sight at all, because there is not even syntax to start with. Set theory is just some kind of blobbish object that has no way to compute that is built in. So in particular, that means that normalization and subject reduction are completely meaningless. They are not here. There's no way to talk about it at all. And this leads me to claim the phenomenological law of set theoretical models is that they really suck. So instead, we're going to go through syntactic models. So let's step back for a while and contemplate the reality. So what is a model? A model is something that takes the syntax of the sort theory as input, that interprets that theory into some kind of low-level language, so it can be category theory, set theory, you name it. It must preserve the meaning of the source in the sense that you don't map true things to false things. And furthermore, what you hope from a model is that it refines the behavior of structures that were not specified, so that you can take advantage of them in order to get new principles. Okay, so this is highly suspiciously familiar. If you think about it for 1 second, you will see that this is a compiler, nothing more. A model is no more than a compiler. So there is a little catch, though, which is that the typical model we can find in the wild is rather an interpreter instead of a compiler, because there is no real separation between the target theory and the host language. When you interpret a proof, then you get something that is blobbish. That was what was happening in the set theoretical model of Presheaves. You don't have much structure. Instead, syntactic models are a specific kind that are more special in some sense, because now there is a clear separation between the target and the host. So it means that if you have a source, a term in the source, you're going to interpret it as not a blob, but an AST in another target theory, in the target theory. So you have 3 systems instead of only 2. And in what interests us today, we'll specifically look at syntactic models where S and T are both type theories. So this is the big picture. A syntactic model is some kind of a compilation phase that takes like a bigger type theory, stronger type theory, S, the source, and that compiles it down into the target theory via a single bracket that translates terms and a double bracket that translates types. And this is kind of subtle if you look at type theories, because it means you must preserve typing by definition, but because we have dependent types, it also means that you need to preserve the equational theory of the corresponding type theory. If you manage to do that, you get a lot of stuff for free. So first, you don't need at all anything that is not type theoretical. You don't need sets, you don't need anything. The meta theory can be quite weak. So this is what I call the monism. You can do everything in type theory and you're happy if you like type theory. In particular, if your target theory happens to be the calculus of inductive constructions, that means that you can implement your model, syntactic model, as a mere compilation phase from the source into Coq. So that means you don't need any other proof assistant. You can reuse all the infrastructure of Coq for your theory. You just have to implement the compilation phase. So that's what I call software monism. And in particular, that means that all the good properties that I was mentioning before, you get them for free. Everything is done at the level of syntax. So you get computation for free, you get decidability of type checking for free, you get the implementation, as I mentioned, you can reuse Coq. So it's a very powerful kind of model. So obviously I was mentioning Presheaves as like the evergreen model that you can see everywhere. The big question is it possible to see Presheaves model as some kind of syntactic model? And you might be asking why today is the right time to talk about it. This is because there have been 3 attempts at making the Presheaves model more type theoretical. One in 2012, with Jabber, Tabarro, and Soso, one in 2016 with Jabber, Levertovsky, Pédrot, myself, Tabarro, and Soso. And those 2 attempts were kind of failures, and I'm going to come back on this right now. But this year, I managed to give a variant presentation of Presheaves that was seemingly compatible with the syntactic presentation I was advocating a few slides before. So the important thing is that all those broken atoms were small steps into the good direction. So 2012. So Presheaves is just a factor from pure to set. Great. So Mathieu Soso here would just say, hold my beer. You just take CIC and replace set that everywhere set appears in the construction of Presheaves, you replace it with type theory. And the question is like, what could go wrong? So let's do it. So just say a category is a record type that is made out of an object type, a morphism type, you have an identity that goes from P to P, you have composition, and you require a bunch of equations on this structure. And what is a Presheaves? Well, that's easy. That's just an index set together with a restriction morphism that satisfies the expected equations, blah, blah, blah. You say that an element is natural morphism, blah, 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 satisfying equations. And there you go. You get a model of Presheaves in type theory. Do you? Well, yes and no, because remember that I said that you have a few equations that you need to satisfy, and these equations are defined in terms of what is called a propositional equation. That is, they are proof terms that correspond to the equations that are stored inside the term. And this is kind of problematic because if you try to look at what it means to be convertible in the source theory, then what you get in the target theory is no more convertibility. Instead, you need to use those equations in a proof-relevant way, so that if M is convertible to N in the source, you only get a proof that M is equal to N, or its translation, in the target. And this means, if you know type theory, that you need to introduce rewriting like everywhere. This actually is a well-known phenomenon that has a dedicated name, which is the coherence hell. And the only reasonable solution that they found in the 2012 paper is that they need the target theory to be extensional. So what does it mean to be extensional? Extensionality is defined in terms of what I call the Santa Claus conversion. So what is it? It says that to prove that M is convertible to N, so in the beta, like the conventional type theory, it's enough to actually produce out of thin air a proof that M is equal to N. And the proof is a real object of the type theory. It's not an algorithm. So it's kind of better than ZFC. You can prove that it has some kind of constructive flavor, but it has obviously indecidable type checking. So you can, to prove that two things are convertible in the type checking algorithm, you can invoke an arbitrary proof construction that like that Turing machine, it can be terminating in that many steps, for instance. And furthermore, it's even worse than that, because if you do this, you actually destroy completely the computational content of the type theory. The mere beta reduction becomes undecidable. You don't know whether you're allowed to reduce a beta radix. And I recommend reading two of Interhalter's PhD if you want to have more details on that horrible type theory. So this is allowing me to claim that syntactic models that target the extensional type theory are not really syntactic models because you don't have this computational nature to the object. And to be more precise, I believe that extensional type theory is not really a type theory because it has no computational content, and there are a few people out there that wouldn't be happy about it. Okay, let's switch to the 2016 version. So just during the end of my PhD, I was talking with the authors of the original paper, and I was telling them, "Oh, so what you're doing is wrong. It cannot work." And they were like, "Why?" It's like, but because it's clear that Presheaves are called by value, and type theory, meanwhile, is called by name. So you're trying to square the circle. And they were like, "What does it mean? That there is no justification for what you said." So let's have a look. So to understand a bit what I'm talking about, you need to have a very rough idea of what is called by push value, which is essentially a very nice way to talk about ethics. Unfortunately, I don't have time to present the call by push value here, so I'm just going to hand wave a lot. But the important part is that Kripke semantics factorizes through call by push value. And how does it do? It's essentially you interpret a value type as a functor, so that's what we do in Presheaves. But by comparison, the competition type is just interpreted as an index set. So you don't have monotonicity as in the Kripke models, or the restriction morphisms as in the Presheaves construction. And importantly, the adjunction, so it's pretty easy to get an adjunction out of this. To go from a functor to an index set, you just forget the additional structure. And to turn an arbitrary index set into a functor, there is a free functorization construction that is essentially quantifying over all smaller objects. So you say that ux at p is for all q smaller than p, x at q. So if you do this, you get a functor relative for free in a way that is actually even compatible with a definitional equation. Okay, so I said that Kripke models factorizes through this construction, and there is a very well-known embedding, or actually two of them, from the lambda calculus, simple type lambda calculus into call by push value, the call by name and call by value one. Once again, I'm not going to highlight the important details, but the important things to observe is that if you compose the Kripke interpretation together with the call by value interpretation of call by push value, then you get this. Sigma rho tau at p is for all q smaller than p, sigma at q implies tau at q. And this is the Kripke interpretation of arrows, and if you forget about naturality, this is also the Presheaves interpretation of the arrow type. So that means, in particular, that the Presheaves are called by value because they decompose through this call by push value push value decomposition. So that means, in particular, that if you look at the equational theory that is generated by this system, what you get is only the call by value equational theory. That is, you have the right to reduce a beta radix only whenever the argument is a value. And this is because this is just because of that first arrow here. The call by value decomposition in call by value by the very definition of call by value only satisfies the call by value equational theory. So here it doesn't matter, but here that means that you only get the preservation of equational theory through the whole translation if you have a call by value equation on the left. Meanwhile, type theory is call by name. And why is that so? Because the one important rule that introduces computation in type theory is conversion. And it says that if you have M of type A, then knowing that A is convertible to be according to a call by name equational theory, and that M has type B, then, if you know that M has type B and that A is convertible to B, then you know that M is type A. And this, the important part, is that this equational property here allows full beta reduction, so you get full call by name theory. And there is a bad news, that is that call by name is not called by value. And this is the reason why when you do Presheaves, you get into this kind of definitional problem. You don't preserve the full equational theory of call by name. So there is an easy solution for that. You just take the call by name decomposition. So if you do this, what you get on arrows is that sigma implies tau at P is now for all q smaller than P, sigma at Q, parenthesis, so this is on the left-hand side of the arrow, implies tau at P. And this is kind of surprising for people accustomed to the Kripke model semantics, because this is not monotonic at all. And there is this quantification on the left that is a kind of weird. But actually it works, and it adapts straightforwardly to the dependent type setting. So by just making this dependent, you get for free a Presheaves model of CC omega into Coq, essentially. So you will note the quotes around the Presheaves model. So CC omega is CIC without inductive time, so you just have universes and dependent functions. And the good news is that if you, in this Presheaves model, you preserve equation on the nodes. That is, if you have two terms that are convertible in the source, then those are convertible in the target. So problem solved, isn't it? Well, you can ask, yes, I have the negative fragment, only functions and universes. What about inductive types? If you look into the model, you will quickly realize that you can implement inductive types, but the model actually disproves induction principles. And the reason is actually quite obvious in retrospective, because this Kripke translation can be seen as an effect in producing translation. So it's some kind of a reader monad that has additional monotonicity requirements. And here, the probability poll says that if you're doing call by value with effects, then you break functions because you have restricted substitution to values. But dually in call by name, now what you get proper functions, but you broke the inductive types. You get non-standard booleans, for instance. If you have non-termination, there are, for instance, 3 booleans, true, false, and bottom. So the inductive types in effectful call by name are not inductive anymore, which is why you don't get induction principles. So, well, this is kind of nice because this is one of the first reasonable examples of dependent effects. So there was an interesting find. But at the same time, it still means that we don't have a syntactic Presheaves model. So let's have a little bit of interlude. So in the years that occurred after 2016, we worked quite a bit on this effectful type theory. So we designed a crapload amount of new translations that would add effects to type theory, and we understood in the process a lot of what we first missed when studying Presheaves. So first observation is that if you look at the standard categorical Presheaves interpretation, you get a model of the full lambda calculus, not only call by value. So even though you require extensional principles, you do have beta conversion unrestricted. So why is that? The reason is that when you look at the interpretation of function types, in addition to saying that A implies B at P is for all Q smaller than P, AQ implies BQ, You also require an equational property, that is a naturality property, saying that f commutes with restriction. And this, we don't have anything similar in the call by name interpretation. But the alleged question is that, well, could be some kind of trick that only works for Presheaves. Like, we don't know, just maybe just an accident. Well, not so much. So this is a completely unrelated slide. Let's consider for a second a call by value lambda calculus. So there is a notion that has been designed by Furman, which is called thinkability. So a term T is thinkable if it satisfies this equation. So this equation says that there are two ways to produce a term of type unit to A. Either you first force T, evaluate it to a value, and store the result inside a thunk, or put directly the term behind the thunk, right? And if you think about this for a few seconds, you will realize that thinkability is an intuitive notion of observational purity, in the sense that T is thinkable if it behaves as if it were a value, because this is like performing all the effects that T can do, and then storing the result as an inert value, and this is just an inert value. So thinkability is really no more than an equational way of capturing purity. The good thing is that it doesn't depend on the underlying effect. This is an equational property that is definable in any call by value lambda calculus. And in a pure language, in particular, all terms are thinkable. All terms satisfy this equation. There is a very well-known, say, realizability result that says that if you take all terms and that you restrict all the subterms to be thinkable, then you get full beta conversion instead of call by value. So, for instance, for a function that says that a function realizes A implies B, whenever for all u that realizes A, not only f applied to u realizes B, but also you require that the term that you introduce here is thinkable. If you do that for every type former, you will get a model of full beta conversion. Okay, now let's look at what it means to be thinkable in the cryptic semantics. Well, it's pretty easy. A term T is thinkable in the cryptic semantics if and only if it is natural in P. Its translation natural in P. So this is kind of magical if you think about it, because that means that Presheaves are nothing more than the pure subcategory of an effectful call by value language, which is the one you get when you just perform the careless crypt key model. In particular, the underlying construction has nothing to do with cryptic semantics. You could do that with an arbitrary effect. You would get the very same result. You would have to replace natural by the corresponding notion of thinkability in the effectful model that you were considering, but that's about it. The problem is that this definition of thinkability in the case of cryptic semantics relies on extensionality, so we cannot apply it to time theory. What could we do to adapt thinkability to call by name and get the best of both worlds? Well, there is a kind of standard counterpart to thinkability in call by name, and this is known as parametricity. So parametricity happens to be applicable to type theory, and essentially what you say is that you duplicate everything. When you have a term M of type A, you get a proof that M is actually well behaved according to the parametricity predicate of A that is defined that way. And at the level of variables, it means that you duplicate every variable into the underlying variable together with a proof that this variable is well behaved with respect to the corresponding parametric predicate, right? It is a syntactic model, so this is nice, and it's in particular compatible with the intentional content of your type theory, and you can see it as a very generic kind of realizability for type theory. So if you apply the thing to the parameter translation to the Presheaves model and call by name, what it means, for instance, for a Boolean variable is going to be translated as a thunk for all q smaller than p a Boolean. So that could be effectful because this is not necessarily a Boolean, it can observe the variable, together with a proof that x is well behaved at p, according to some predicate on Booleans. So to recover dependent elimination on these Booleans, so we need to ensure that this is really a Boolean. We need to be able to prove that if x is well behaved according to a Boolean, then this is a constant true or a constant false Boolean. Otherwise, it would be an effectful boolean that would be broken. But we need to be, in order to satisfy the good equational properties, you need it to be correct in a unique way. That is, there is only one way to be a correct boolean. It's a hot proposition. But at the same time, because b epsilon is indexed by p, it also needs to be compatible with the Presheaves structure. So in particular, you need to be able to equip it with restriction morphism, saying that if x is compatible at p along the Boolean property, then the lowering of x along alpha is also compatible at q for the same parametricity predicate. And furthermore, you need definitional functionality. That is, that you need this to commute on the nose with the composition and identity. Otherwise, you get coherence again. And this is kind of terrible because this is exactly the call by value versus conundrum one level higher. So what happens if you pick the predicate that says I am either left or right? Then you get unicity, good, but you break definitionality, so you're called by value. But you can also do the free construction by freeifying everything on the fly. So you universally quantify over all Q. This will give you definitionality of the functoriality. But now you're going to break unicity. There is no way that this proof is going to be unique. It could be actually observing the Q it is given here. So the thing is, you cannot get both at the same time in CIC. So you're kind of stuck. You could solve that using infinite towers parametricity by saying that each level is ensured to be correct at the upper level, but then you would be doing typical type theory, and this is essentially justifying the same theory using Presheaves. So what would be the point of using Presheaves to justify Presheaves? We need something else. So we're blocked in that problem when suddenly there was a popular paper last year that introduced a new sort of strict propositions. So S-prop is a sort that says that whenever A is a type that is called a strict proposition of type S-prop, if I have two inhabitants of A, M, and N, then I know that they are equal. So you can really see it as some kind of subset of prop in hot that is compatible with hot and that has all the good properties. The important point is that the strict proposition sort is closed in their product. So if you have X, if B is a strict proposition parameterized by some X, then the product of this is still a strict proposition. And at the level of inductive times defined in the strict proposition thingy, is then you can only eliminate falsity, not other inductive times. They discuss an extension of that theory that we will call SCIC, that in addition to eliminating false, you are also able to eliminate equality from S-prop to type. And this is called in the column sort of part as a strict equality. In particular, that means that any two proofs of equality are definitionally equal. So it has definitional IP. And the way I like to phrase this is that hot is some kind of libertarian approach to type theory. You freely add all these infinite towers of equality, and when you want more equality, then you require equality one level higher, and you push that ad infinitum. Meanwhile, the strict CIC is following the path of authoritarianism. It will guillotine all high equalities. There is nothing more above the first level of equality. All humans are born uniquely equal in rights. This is the missing part of the first article. So if you use strict equality, you can see it as the authoritarian way to solve the coherence cell. And you can apply it to the Presheaves construction by tweaking the parameter predicate in order for it to be free. So you get, so that's what we were doing before. You can get definitional functoriality by making the parameter predicate free. But since you have strict propositions, you can also ask it to be a strict proposition. And this will give you proof uniqueness for free. So what does it look like? So as before, the term A is preceded as for all Q's more than P add Q. But now the parameter predicate is also universally quantified for all Q's more than P blah, 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 alpha composed with X. And you require that alpha epsilon here is a strict proposition. So you will get proof uniqueness by construction. And we call this result the Prefacious translation. And you can see that it is actually a syntactic model of CIC to strict CIC that enjoys full conversion, so we're happy. We have full implementation, so that's fine. And the construction is somewhat slightly more complex, but this is really, the idea is just to give off. So did we get anything? So strict CIC is actually weaker than ETT in some sense. So it's only conjectured to enjoy the good syntactic properties. So it seems to satisfy canonicity quite easily, but it's kind of involved in terms of reduction. It is problematic from a point of view of strong normalization, because it's known that if you have an implicative universe plus SCIC, then you are not strongly normalizing, but you're still consistent, so not that problematic. And we don't need implicativity, so it should be fine for our uses. Okay. So it so happens that sets are also a model of strict CIC, so you can present the Prefacious model as a model in set theory. So I'm not going to give the details, but essentially the idea is that you get something that doesn't look really like the Presheaves construction, but it's much more realizability-like. It's not about equational theories of naturality and whatnot. It's really about preserving predicates. Okay, so the result is that the Prefacious model applied to set theory gives a category that has definitional laws, and furthermore, as categories, the Presheaves and Prefacious sets are equivalent. You need extensionality to prove that, obviously, but somehow that means that in an intentional setting, Prefacious sets are better behaved. And I think it's probably good for higher category theory. All right, in the few minutes that are left, I'm going to look for an application of this Prefacious construction by doing a bit of Russian constructivism. So the Russian constructivist school is some kind of a splinter group from the usual constructivism approach. And the main belief is essentially that any proof is a clean realizer from clean realizability. So in particular, there is one specific principle that puts them apart both from Brewer radical approach and Bishop minimal approach. And this principle is Markov Principle. So Markov Principle says that if you have a function from nat to bool, and you know that it's not true that there is no integer such that f of n is true, then actually you can extract an integer so that f of n is true. Okay, so this is not valid in Bishop intuitionism, and this is incompatible with the Brewer point of view as well. So it has a lot of equivalent statements in the literature, depending on the exact knobs or presentation you stick to. So, for instance, that a Turing machine that doesn't loop terminates. That's one way to phrase it. And it's kind of semi-classical. That is, you know that it's strictly stronger than HA omega, and it's also strictly smaller than piano arithmetic omega. But it has a good property that is known in the literature, is that it preserves the existence property. That means canonicity for us in the type-theoretic setting. So the question is, what if we tried to get a model of CIC with MP via some kind of syntactic model? So let's look at the realizer from clean irreducibility. So how do they realize this Markov principle? Essentially what they are doing is that they pick F, they drop the proof, and they start doing an unbounded loop. So they try f of 0, if it's true, then they return 0. Then they try f of 1, if it's true, they return 1, and so on and so forth. Clearly, to prove that this realizer that is doing an unbounded loop realizes MP, you need Markov principle in the meta theory. So this is somehow cheating, because you imported some principle from the meta theory inside the object theory without really providing a reasonable way to grasp it. And in particular, the realizer is stupid. It doesn't use the doubly negative proof. And we need to implement the realizer. You need arbitrary loops. So in particular, Turing complete realizer language. So this is kind of bad. If you want to do that in CIC, we're going to have trouble. So this is not a reasonable way to implement Markov principle in CIC. We need to find something else. The good news is that there are two alternatives, not one, but two. So the first one is a syntactic model, actually, from Decomposition that applies to Heiting arithmetic with the higher order types. And the other one is the direct file proof that uses static exceptions by Herbelot. So if we focus on the Decomposition model, you can see that's kind of a mix between Kripke semantics and Friedman's A translation. So in terms of functional power, Kripke semantics is some kind of a reader with a global cell. So the global cell has type not to bool in this model, where Being smaller means to be truer pointwise. That is, the function, the top element is the function that is false everywhere, and you become smaller by putting some true values at some indexes. And the A translation computationally corresponds to adding exceptions. And here the exceptions are actually, the type of exceptions is parameterized by the current global cell. And the exception type as type, there exists an integer so that the current cell is true on that integer. And what makes the model work is that critically this exception type depends on the current cell value. So you have exceptions whose type depends on the context you're living in. In particular, observe that if you're in the top context, when P is the constantly false function, then there are no exceptions. So there's no way to raise an exception when you are at top level. So I claim that this model is kind of ad hoc. So I'm going to present it, or at least sketch it very briefly, as the composition between two syntactic models. So the first one is going to be the Prefacious model I've been describing before, and the other one is called the Extensional Model, which is the equivalent of A translation in CIC. And this results in what I call the calculus of constructions with completeness principles, because Markov Principle is typically used to get completeness principles for a lot of logics. And because we presented all these this model as a composition of two translations that for free, we get the good properties, assuming that strict CIC satisfies the good properties. And I'm not going to describe the exceptional model, but it's really a very simple syntactic model that essentially states that you interpret a type as a type together with a function with that allows to raise an exception on the type. So an exception is type E, and you need to be able to raise exception of that type. So in particular, if you look at the interpretation of negation, you get that the interpretation of negation is isomorphic to the relativized negation, where you replaced bottom by the type of exception. And we're going to do the very same thing as in the Coco-Hoffman's model, that is by picking the type of exception to be an exotic type that only exists in the Prefacious model. And this exotic type is defined the very same way, that is, E at P is just going to be, there exists an integer so that the current cell is actually true at that integer. We can define a modality in this extended type theory. So we're leaving the middle one here. We have three theories, so it's a bit hard to understand. We're in the middle theory here. E lives in the middle theory. And this modality lives in the middle theory as well. And essentially, this says that you can push the knowledge that a function has a point where it's true somewhere. And this is a modality, so it's equipped with a return function. It commutes with the arrows and paths types. And importantly, the relativization of E is E plus the proof that the relativization you've been using is true at some point. And you can implement now Markov Principle in the CCCP model by just doing the simple pushing of the translation of Markov Principle in here and using the property I was mentioning before, that is relativized negation. And there is nothing more to it. And if you try to interpret this in a computational way, then there is a straightforward way to understand it. That is, essentially, every time you go under a local modality, then you enrich the type of exceptions. Because, as I said, local phi E is E plus this. So every time you go under a local, you can raise new exceptions. And this means that return of this modality is nothing more than some kind of delimited continuation prompts for some kind of static exception binder, right? So every time you cross a local, you are able to raise new exceptions. At top level, you have no exceptions because E has no proof, no empty proof. But it so happens that inside some contexts, you can enrich the type of exception you're working with. And if you look at Herbelin's proof of the Markov Principle, then this is literally the same thing. It's doing the very same thing as the proof I gave in the exceptional model. That is, it sets a handler, which is essentially the same thing as return, and applies it applies the function not there exists to a continuation that raises an exception, essentially. And this is literally what the other principle is doing in the other model, except that we did it in the full-blown CIC language in a way that is compatible with the equational theory on the nose, so that we get for free a full model of CIC with a Markov principle that is computational, canonicity, so on and so forth. So somehow, this proof is no more than the direct style variant of the Coco-Hoffman's model. Just to digress, last slide of digression is that this construction, using exceptions plus Presheaves, is very reminiscent of normalization by evolution models. So if you know about normalization by evolution models, you know that you have to do something when you want to interpret positive types in the model. And the typical way to do that is to add neutral terms to their interpretation. So typically you say that a boolean is not going to be true or false. It's going to be true, false, or a neutral term. And if you do that, you'll see that there are no neutral terms inside the empty environment. So at top level, there are no neutral terms. You know that the boolean is boolean. And at the inside a context, you can create new neutral terms. And if you look inside the computational content of the normalization by evolution model, you will realize that those neutral terms behave really as if they were exceptions, and they are handled by the binders that are introducing them. And the alternative way to get completeness for positive types, instead of having to add neutral terms, is to have Markov Principle and the meta theory. So this indicates that these two things are very similar in spirit. There is really something going on with this construction that is similar in both cases. Also, because I said that somehow we emulated some kind of one-shot delimited continuation with Presheaves and exceptions, this probably indicates that there is a link between delimited continuation and Presheaves in a way that can be exploited. I don't know more about this. If people in the audience know, I would be delighted to hear about it. Right, so let's conclude. So what did we do about Presheaves? So we showed that Presheaves are pure fragments of an effectful call by valid language that corresponds to some kind of reader effect. And if you go through the call by name route, then you get a beta behave presentation that is compatible with the beta conversion, so that is better for dependent type theory. But you need parametricity defined in terms of strict equality to be able to define this as a syntactic model. So it's not completely satisfactory because we don't know about the good properties of CIC, although they are conjectured. So still a bit of work to do. And on Markov Principle, then we gave a computational interpretation of it in dependent type theory, so full-blown dependent type theory, in terms of exceptions whose type depends on the context, thanks to the Presheaves construction, essentially, and everything computes as expected. So the thing we want to do is to implement cubical type theory using the Prefacious construction so that we can use Coq as the ultimate proof assistant, so that we would be able to directly implement cubical type theory in Coq without changing its kernel. That would be very nice. Thank you. I'll be happy to take any questions, and I hope I'm not too late.
Thank you, Pierre-Marie. I'm sure everybody's clapping behind their cameras right now. Thank you for the informative and entertaining talk. For everybody, please ask your questions in Zulip or the Google Meets. I'll start out. I have a question from Ohad, where first I'll read it verbatim. Okay, so Ohad says, I'm super confused by the theorem about naturality. I thought every term in a Presheaves model denotes a morphism, i.e. a natural transformation. What am I misunderstanding? So I believe that's about the part where you added the condition of naturality to the model.
Yeah, so I'm not sure I understood the question properly, but essentially you can do Presheaves with that naturality. That will give you a model of call by value, right? And not call, it doesn't satisfy beta laws. But if you look at what it means to be pure in the model, this is exactly naturality. So I'm not sure I can really rephrase that in a simpler term. So maybe Ohad has more Keynote.
Yes, Wouter, the slides will be available later.
Yes, I will.
Oh
yeah, so there's a paper that is mentioned in one slide. That's the last week's paper.
Great. So yeah, we'll share that on the Zulip and yeah. And yeah, maybe you and Ohad can talk about this on Zulip or later. Right. Yeah. Oh, so I had a question actually. So there's one part you said that the so the thunkability of terms in this unnatural model where the pure terms, the thunkable terms were exactly the natural transformations. But I was wondering, what about there's a dual notion of thunkability for call by name, which is linearity.
Right.
Is that also an interesting concept in that model?
I think so. So we tried to do a model with linear terms instead of in call by name with linear terms of thinkable terms in call by value. So essentially, it's not as well behaved in terms of intentional content as parametricity, although you essentially get the two same things in the end. But the interesting part is that linearity turns out to be very important when you do dependent type theory with effects, because all the models we have so far satisfy a restricted form of dependent elimination. So when you want to prove, say, a property about booleans, so P, say you have P from bool to type, and you want to prove P of B for any boolean B, so usually it's enough to prove P true and P false, right?
Mm-hmm.
But in presence of effects, this is not true anymore. You need to restrict the rules. And the thing is, all the models we have so far, if you restrict the predicate to be linear, in the sense of the linearity from call by name, so that's an equational property, then actually dependent elimination becomes true. So dependent elimination is only true for those predicates that are not observing the effects of the underlying term.
Okay, great, that makes sense. I have another question, this one from Christopher Jenkins. He said, could you reiterate the point you made earlier in the talk that extensional type theory is not, in your opinion, true type theory? Yeah,
right.
That's maybe a controversial statement.
Yes, that's a question I was waiting for. I'm sorry that Andre is not taking it seriously. Right, so essentially this comes from my background. I'm a computer scientist, so I believe that programming, in particular computation, comes before logic, right? So this is kind of the Girardian school. You can define logic first. The computation is pre-existent to logic. You have Turing completeness. There is no such thing as completeness for logic because of Gödel incompleteness theorem. So if you destroy the computational content of your type theory, then somehow you're not doing anything that constructive in the sense that it's like when you do CZF, like you don't have a way to really trust your model. Somehow you still have to trust. So it's more a philosophical question than a technical question. But it's really about what you can expect from your proofs. And you know that when you have a system that has a computational content built in, then you don't really have to trust your proof that much. You know that if you have a sigma 01 formula, then you can compute and get something that you can observe. And if you have a type theory that has no computational content, then it becomes some kind of rewriting system that is not as trustworthy, I would say, as a type theory. So it's kind of throwing the baby with the bathwater when you do ETT instead of TT. I know this is some kind of a very strong restrictions from myself, but this is really some kind of a foundational point of view.
Okay, well, I'm sure that could be discussed more by both of you. Okay, and I think let's have one more question. This one, let's see, from Vikraman Chowdhury. He says, my favorite thing about Presheaves is their universal property, i.e. the free co-completion. Is there a computational story behind that universal property?
Good question. I don't know. But if I had to guess, I think this somehow comes from the target type theory or the set theory you take. This is where it comes from, I would say. I don't know, but I think it's an interesting question.
Okay, well, since that was fast, I'll have the one other outstanding question from Andre Bauer. He says, does SPROP have computational content? And if not, how is SCIC a type theory?
So, yes, it does. We know how to reduce the term. The problem is that it's not clear that it's stronger than normalizing. So, but at least it seems to be, I think, confluent. And we believe it has canonicity. I mean, we don't have a proof of that. So, if the term reduces, then you know that you can extract something out of it.
Okay.
So yes, I agree. Well, while this question is not settled, it's not quite a true type theory. So not yet.
Okay. Okay. Well, thank you, Pierre-Marie. So with that, we're going to take a break. Next talk will begin at the half-hour mark. But I'll leave the meeting open so people can discuss the talk. And thank you.
And I'd just like to mention that you can also meet on gather.town. I've posted the URL in the announce stream.